Hello students. In this video we're going to continue on with our nomenclature series and discuss the first of the three categories, A, acids. And you may recall that I've introduced the three categories as A, acids, B, ionic compounds, and C, covalent compounds. But in this chapter, I've chosen to discuss them in reverse order. And the reason for that is because the C, covalent compounds tend to be easier to name, and students tend to remember those better from their previous chemistry course. So we cover those first, and then we moved on to ionic compounds, in which we learned the 34 polyatomic ions that you need to know for this class. And now we're going back to deal with the A acids, because for acids you need to know the polyatomic ions. So to review, acids are usually the easiest compounds, the formulas to spot, because they always have hydrogen in the first position, the initial position in the formula, and an aqueous state indicator. Now, as you continue on in your chemistry courses and in your supplemental reading, you may see the formula for an acid that does not have an aqueous state indicator. However, for this course, I'm going to stipulate that all acids need the aqueous state indicator, because there is a difference between an HCl, for example, that does not have an aqueous state indicator. That would be just a hydrogen chloride, a covalent compound. But by including the aqueous state indicator, we signify that it has been dissolved in water, at which point it becomes an acid. And so it takes a different acid naming convention. So again, acids, for the purposes of this course, will have a hydrogen in the initial position in their formulas, and they will have an aqueous state indicator. Similarly, we will not see a charge written on the overall acid formula, for example, down here. And that will be the clue to tell us that we're not looking at a polyatomic ion that just happens to have hydrogen in its formula, like those we learned in previous videos where we had hydrogen carbonate, hydrogen sulfate, and so on. So once we have identified that a formula is an acid by the H in the first position and the aqueous state indicator, then we have a rule set with 3 rules that will guide us on how to name the acid. However, in contrast to the other 2 categories, the ionics and the covalents, for acids we do not use all 3 rules. For acids, we only choose one rule, and the rule that we choose is going to be determined by the name of the anion. So, we must learn the polyatomic ion names because it is the ending of the anion's name that will tell us which of these 3 acid naming rules we have to follow. So just to emphasize, it is the ending of the anion's name in the acid that will tell us which of these 3 rules to follow. And we're only going to be applying one of these rules, and it will be based on the anion's name. So, this first rule is for acids where the anions upon which they are based end in the letters IDE. So here's a good example. A, is this an acid? Yes, hydrogen and aqueous. So this is an acid. So since it's an acid, we know that we need to determine the name of the anion. To do that, we break the acid apart so that we remove the hydrogens and we leave just the anion. So the formula for the anion is going to have a charge, and the charge is going to be determined by removing those hydrogens, and every hydrogen that we take away will remove a positive charge with it. So if I remove one positively charged hydrogen, then I leave a single negative charge behind. So there is the formula for the anion upon which that acid is based. And I hope you recognize this as the monoatomic ion that is formed when a chlorine gains an electron to become the chloride ion. So now we have identified the name of the anion. And we can see that the name of the anion ends in IDE, and so we know it's going to use this first rule. Well, this first rule says that if you have an IDE anion upon which the acid is named, then the acid name takes a hydro prefix, HYDRO, then the root word from the anion, and then an IC ending. And then we add the word acid. So it's a hydro prefix, root word, IC ending. To determine the root word for the anion, usually we just eliminate the last three letters, whatever they are. There are two important exceptions to this. And the important exceptions are down here at the bottom of this page. Root words for sulfur-containing and phosphorus-containing anions, these are the root words. They require 2 syllables. So the root word for a sulfur-containing anion is sulfur. The root word for a phosphorus-containing anion is phosphor. Those are the special root words for those special cases. Otherwise, we just remove the 3 letters at the end. So in this case, the root word for this anion is CHLOR, chlor. So we plug that into the gap here, and this becomes hydrochloric acid. Hydrochloric acid. Hydrochloric is all one word. Acid is a separate word. Okay, so again, what we just did, we identified this as an acid. Then we determined the formula for the anion upon which the acid is based. Once we did that, we determined the name for that anion. We looked at the last 3 letters for the anion's name, and based on that, we chose the rule to use. Since this is an IDE ending, we're going to use Rule 1. And Rule 1 says that the acid is named with a hydro prefix, the root word for the anion, and an IC ending, and then the word acid. So I've given you 2 more examples here, and I would like for you to try these. Don't forget that sulfur and phosphorus containing anions follow this special rule for their root words. Okay? So I would like for you to fill in these 3 boxes for H2S aqueous and do the same down here for HCN aqueous. Pause the video, complete those rows, and when you're done, resume the video and I'll work through this with you. All right, returning to these examples, we have H2S aqueous. This is an acid, so we're going to use our acid naming rules. That means we have to know the name of the anion to determine which rule to use. To determine the anion's name, we determine the anion's formula first. So we remove those 2 hydrogens. Each hydrogen takes a positive charge away with it, and it leaves us with the S with a 2- charge. This is a sulfide ion. Since it has IDE as the ending, we know that we're going to use Rule 1 for naming the acid. So the name for the acid has a hydro prefix, the root word from the anion, and the IC ending. So the hydro prefix, the root word for the anion, since this is a sulfur-containing anion, the root word is sulfur. So the root word here is sulfur. And then an IC ending, and the word acid. Hydrosulfuric acid. Moving on to the next example, we have HCN aqueous. A, is this an acid? Yes, it is. So we're going to use acid naming, which means we have to know the name of the anion upon which that acid is based. So we determine the anion's formula. We remove the hydrogen. By removing 1 hydrogen, it leaves a negative charge, and you may recognize this as the cyanide ion. It is one of our polyatomic ions. The ending is IDE on the anion, so we know that we're going to use Rule 1 to name the acid. Hydro prefix and the root word from the anion, which typically is whatever is left after we remove the last 3 letters. C-Y-A-N in this case, and an I-C ending, and the word acid, hydrocyanic acid. One quick note about this first rule, IDE anions. Most of the IDE endings for anions arise because we have a monoatomic anion. So it's a chloride or a bromide or an iodide, for example, and that's where we typically get the IDE endings for the anions. However, you will encounter the occasional exception where we end up having a polyatomic ion which has an IDE ending. So that's rule 1. And again, if the anion ends in an IDE, then you are only going to use rule number 1. You're not going to use rule 2 or 3. Now, moving on to rule 2, let's take a look at what rule 2 says. Rule 2 says look at the anion name and look at its ending, and if it is an ITE, then you're going to use the rule 2 naming convention, and that says that the acid is going to be named according to this pattern. You will have the root word for the anion and an OUS ending, and then the word acid. So let's take an example here. H2SO3 aqueous. Is this an acid? Yes, it is. So we need to determine the name of the anion upon which it's based. So we remove the 2 positive hydrogens, and that leaves a 2 negative charge on the anion. So the anion formula is this right here. And you may recognize that this is following the pattern of the sulfate-sulfite. This has 1 less oxygen than the sulfate. This is the sulfite anion, and indeed it does have an ITE ending. Since the anion has an ITE ending, we are going to use rule 2 to name its acid. So we need a root word, and since it's sulfur-containing, it follows the special convention where the root word is sulfur. And then we add the OUS ending. So this is sulfurous acid by following the Rule 2 acid naming convention. So with that in mind, I've got 2 more acids here that also have the ITE ending in their anions, and will follow this rule. I would like for you to complete these 2 rows. You may need to consult your notes to determine the names of the anions that we have here, and if you need to, that's okay for now. But eventually you're going to need to know those polyatomic anions well enough so that you don't have to consult your notes to determine their names or formulas. So go ahead and fill in these 2 rows, pause the video, and when you're done, resume the video and I'll work through those. Coming back to this, A, is this an acid? Yes, it is. So I determined the name of the anion, and to do that I need to determine its formula first. So I remove the hydrogen takes away a positive charge, and leaves this as the anion's formula, okay? Oops. The hypoiodite, sorry. Ion, HYPO IODITE, hypoiodite. It's 1 oxygen less than the iodite, which is itself 1 oxygen less than the iodate. So here we have the hypoiodite ion. Notice that this prefix hypo, HYPO, is not the same prefix that we used up here, hydro. We will never encounter hydro and hypo in the same acid. Hydro prefixes only happen when the IDE ending is on the anion. Hypo anions only have ITE endings. So this is the name of the anion. It's the hypoiodite anion. And we are now going to use that to determine the name for the acid. So what is the root word here? We remove the last 3 letters, the ITE, and we get this root word, hypoiodite. And there's our root word after we remove the last three letters. And then we add the OUS ending. So yes, this was a little tricky because it had a hypoiodite anion, and that may have thrown you a little bit in how to determine its root word. But it follows the same pattern. You take the last three letters from the name of the anion and use that as the root word. Then you add the OUS ending. So this is the hypoiodous acid. Hypoiodous acid coming from the hypoiodite anion. And the last one here under Rule 2, HBrO2 aqueous. A, is this an acid? Yes. Let's determine its anion formula. We remove one hydrogen, and we are left with this formula for the anion. The name for this anion is the bromite anion. It ends in ITE, so we are going to name the acid based on the Rule 2 convention. So we have a root word plus OUS. The root word here, after we remove the last three letters, is brome. So the root word is brome, and then an OUS ending. So this is bromous acid. And those are a few examples for how we use Rule 2 for naming an acid when the anion ends in the letters ITE. Moving on to Rule 3, now we have a rule that talks about acids that are based on anions that end in the letters ATE. And the naming convention here is we have a root word and then the letters IC, acid. And I want to take a moment here to contrast this with Rule 1. Rule 1 also has root word and then IC at the end, but there's a hydro, HYDRO prefix. So what distinguishes the names between Rule 1 and Rule 3 naming conventions? Hydro is used for Rule 1, but not for Rule 3. So I'll do the first one. Let's determine the anion's name, and to do that, I determine the anion's formula first. So I remove a positive hydrogen, and that leaves NO3 with a negative charge. That's the nitrate ion. The nitrate anion. I can see that it is an anion that ends in ATE, and so it's going to be using this Rule 3 to determine the acid name. So I have a root word and then an IC suffix. The root word, after I remove these three letters, NITR, nitr, is the root word, and then IC as the ending, acid. So I've got nitric acid. So there we go. That's an example of how to use the ATE anion rule, root word IC, acid. So I've got two more examples here. I would like for you to work those through. Pause the video and do that, and resume the video when you're done. All right, coming back to this. A, is this an acid? Yes. Let's find out what the name of the anion is. So let's figure out what its formula is first. Remove the positive hydrogen, and I'm left with this anion. The name for that anion is the periodate. Anion. It ends in ATE, so I will be using the Rule 3 convention to name the acid. So I use the root word by removing those last three letters, and it's period. O-D, P-E-R-I-O-D. Period is the root word, and then the last two letters, IC, acid. So I have the name of the acid. This is periodic acid. Yes, it's spelled the same way as the word periodic, but it's pronounced periodic because it comes from the periodate anion. My last example here is one of the most common acids that you will encounter, and this is an acid. Yes, it is. I remove the two positive hydrogens, and I'm left with this anion. The name of that anion is the sulfate anion. It ends in ATE, so I use Rule 3 to name the acid. So root word IC. Sulfur-containing, so the root word is sulfur. And then I add IC to the end, and the word acid, and I get sulfuric acid. Now you may notice that I've given you an example of a sulfur-containing acid in each of these rules, and I did that intentionally so that you can see how we can have acids that have fairly similar formulas: H2S aqueous, H2SO3 aqueous, and H2SO4 aqueous. And they have different names: hydrosulfuric acid, sulfurous acid, and sulfuric acid. So this is a really good example about why we have these nomenclature rules to begin with, because there are a lot of compounds that are very similar in their formulas, and we have to have a rigorous way to be able to communicate about them so that our readers or our listeners know exactly which chemical we're speaking about. And so we have nomenclature rules that allow us to follow certain patterns, and therefore we can communicate clearly about things that are otherwise fairly similar. Okay? Last comment is to remember special root words, sulfur and phosphor. So keep those in mind as you think about the root words that you need to use for acids that are based on anions that contain sulfur or that contain phosphorus.